So we are still doing energetics, and what we're going to talk about is now enthalpy changes of solution, delta H solution. What's the definition? What now in this is known as standard enthalpy change of solution. So what happens in this thing? What happens is that you simply, I mean, you studied this in AS as well. What happens is you simply dissolve a substance, any substance, whatever the substance is, as long as it mixes. Like 1 mole of NaCl solid dissolves in water and turns into NaCl aqueous. Okay, that's it. You dissolve 1 mole of substance. The substance has to be 1 mole at all cost. So the substance needs to be 1 mole at all cost. You dissolve it and you get and whatever energy that's released or absorbed during this process, that's known as the enthalpy change of solution. For ionic compounds, remember ionic compounds dissociate. So there's another way of writing NaCl aqueous, and that is Na plus 1 aqueous and Cl minus 1 aqueous. You can write this in dissociated form. And for ionic compound, what basically happens is that when you mix an ionic compound in water, but we're going to talk about that later on. I'm just describing what enthalpy of solution is. So any substance, whether it's ionic or not ionic, I mean, you can talk about ethanol. So ethanol is C2H5NOH, and it's liquid, but it can be, if 1 mole of it is dissolved in water, it turns aqueous. So it becomes C2H5OH, and it's now aqueous. So whatever the enthalpy change for this thing is, it's going to be called the enthalpy change of solution. Does anyone know whether it's exothermic or endothermic? Any idea?
The endothermic.
It's actually both. TK, it could be endo, it could be exo, both. When you're trying to resolve a substance, sometimes energy is required, sometimes energy is given off. For example, if you dissolve HCl, it's highly exothermic. Like if you make an HCl solution in the lab and you try to add water to HCl, a lot of heat energy is produced. So it depends, because both bond breaking and bond formation is happening during the process. So remember enthalpy of solutions. If it's exothermic, that means it dissolves easily. That means not a lot of energy is required to dissolve it. I mean, you absolutely don't require any energy. Energy is given off actually, and it dissolves easily. And it's going to be more soluble at lower temperatures. Exothermic reactions are going to be more. The substance would dissolve even more at lower temperatures. And similarly, enthalpy of solution could be endothermic as well. So enthalpy of solution could be endothermic, and in that case, it doesn't dissolve easily, which means it's kind of insoluble. So if it's or it dissolves with difficulty because it requires heat. Until and unless you don't give it heat, it's not going to dissolve. So it's going to be more soluble at higher temperatures. So endothermic processes, they are more soluble at higher temperatures. So now the point is, why is it endo? Why it could be endo or exo both? Because it involves both bond breaking and bond formation. Anything that involves both things usually can be both. Like if it requires a lot of energy to break bonds, then it's going to be endo. If it requires a lot of, or it releases a lot of energy during bond formation, then it's going to be exo. So it involves both bond breaking and formation. I mean, one example that I can think of is think of ethanol dissolving in water. What happens? Like you have ethanol molecules. So ethanol. Let's talk about methanol actually. So methanol molecules, and let's say you just have exactly two methanol molecules. There's a solution, and that has exactly, just for simplicity, it has exactly two methanol molecules. So the methanol molecules will have intermolecular forces. And they would be attracted to each other. There's going to be hydrogen bonding. H is going to be strongly positive. There's going to be a lone pair on O, which would make it partial negative. And here's your positive H. Here's your lone pair. Okay, that's going to be partial negative. And they would be strongly attracted to each other. So that's ethanol molecules. Now, when you try to dissolve it in water, and whenever we talk about enthalpy of solution, we basically mean that we are trying to dissolve it in water. So once I bring in water molecules, the problem with water molecules is that they are also forming hydrogen bonds with each other. So here's your water molecule, and you've got lone pairs, and the H is positive, and they are attracted to each other, right? So for them to mix, the first thing is you would have to get rid of the old bonds. So you would have to break the old hydrogen bonds. I mean, and both of these hydrogen bonds are going to be kind of different. I mean, this hydrogen bond between ethanol molecules would be slightly different than the hydrogen bonds between water molecules, right? So the first step one, when you're trying to dissolve, you break the old bonds or whatever the intermolecular forces are. Because that's number one. You break those bonds, and so let's say I have, and how do I do that? I stir. Okay, that's why you stir things. You stir things so that molecules kind of mix up. Once they have mixed up, so the bonds are broken, and because of my vigorous stirring, the molecules are now all over the place. For example, this molecule is over here now. This water molecule is somewhere over here. This water molecule is over here. Okay? So they've mixed up because of my vigorous stirring. And now they're going to form new bonds. So new types of hydrogen bonds are going to be formed between them. So the partial negative of O of ethanol would attract the water molecule. The lone pair on oxygen over here, partial negative, would attract the H in the ethanol, and so on. Uh, I mean, this H would be positive, so it would be attracted to the lone pairs over here. This partial negative lone pair would be attracted. So now new bonds are formed. So no matter what type of dissolving is happening, the first step requires you have to get rid of the old bonds, whatever those are, whether it's intermolecular forces or bonds. You would have to get rid of those, and then you form new bonds. Is this point clear?
Yes, sir.
Yes.
Okay. And and remember, different substances have different things. Like ethanol and water, they're going to have hydrogen bonds. If you have ionic substance, they're going to have ionic bonds. You would have to break those ionic bonds. I mean, this is exactly what's. And let me show you. This is what's going to happen for an ionic substance. And this is what's kind of more important, because we're going to talk about this in a bit more detail. So we're going to talk about how ionic substances dissolve. And that's why you stir things, because you have to get rid of the old bonds. So ionic compound, ionic solid dissolving, crystal dissolving. So what happens in that case? Ionic substances have ionic bonds. So you've got NaCl that has Na plus one attracted to Cl minus one, which is then attracted to Na plus one, and so on. So they are all attracted to each other. So that's your crystal. Okay, that's your tiny crystal. I'm going to put that crystal in a bowl of water. So let's say there's this beaker and that's full of water, and I'm going to mix vigorously. And when I do that, all the ions, they dissociate, they get scattered, and your water now contains Na plus one that's dissociated. Cl minus one is separate. There's an Na plus one and the Cl minus one. They're all uh, going in different directions. So you have to break. So the first step is you have to break the ionic bonds. So you're going to break the ionic bonds. That's the first step. And what type of bonds are formed? The water molecules are going to come in. So you're going to have all these water molecules that are going to come in the way, and there would be lots of water molecules. Like they're going to be everywhere. Okay, so the water molecules are going to prevent the sodium ions and the Cl ions to join up again to form the crystals. So what are the new bonds formed? The new bonds that are formed are, I mean, that's the second step. The new bonds formed are with water. So what actually happens is that when we think of Na plus 1 aqueous, like Na plus 1 aqueous means, so what is it? I mean, we always write that NaCl dissolving. What happens? When NaCl dissolves, we write that NaCl is aqueous, or we just write that Na plus 1 is aqueous and Cl minus 1 is aqueous. This equation is not entirely true because there is no such thing as Na plus 1 aqueous in reality. What actually happens is that the Na plus 1 is not just independently swimming around with water molecules. What it actually does is that it actually bonds with water molecules. Like you have an Na plus 1, and an Na plus 1 has six sides. Let's assume there's six sides. There's a top, there's a bottom side. Uh, I mean, like if you are standing in the middle, it's top, bottom, front, back, right, left. So you've got six sides. And so that's your x and your y axis. So what this Na plus 1 would do is that it would start to attract water molecules because water molecules are highly polar. The oxygen in the water molecule has this very highly electronegative lone pair. So it has this highly electronegative lone pair. And that lone pair would be very strongly attracted to the positive ion. So the water molecule is going to be sticking or bonding with the Na plus 1. It won't be just, so the Na plus 1 is not just randomly moving around. Like it's not, I mean, this is not what's happening. I mean, the Na plus 1 is not just moving with the water molecule somewhere. It's not Na plus 1 aqueous. It's actually Na plus 1 bonded to water molecules. I mean, these water molecules are all sticking to Na plus 1 and they're tightly bound with it. And from all sides, water molecules are going to come in. And from all sides, these water molecules and the lone pairs would attract, would be attracted to these sodium ions. So you just let me draw all of this.
Sir, in this part, like the water molecules are still water molecules. Like when would this happen that we have H plus and OH minus ions separated? Like why is water compound still there? Why doesn't this happen?
Why doesn't it ionize?
Exactly, when does it ionize?
It can actually ionize in this case as well. Because what's going to happen is, I mean, if you add NaCl to water, the water doesn't really ionize that much. Okay, that's, I mean, the first thing is water doesn't really form H plus 1 and OH ions. What you studied in O levels, that water ionizes. It ionizes very, very weakly. It doesn't really do that. I mean, it's like if you have 1 million molecules, a few molecules would ionize, not a lot. But adding NaCl would actually increase the ionization. And the reason for that is, like, if all these water molecules they come in and they form these dative bonds. I mean, these are dative bonds. Why are they dative bonds? Because Na plus 1 is not contributing any electrons. It's just pulling the electrons from the oxygen towards itself. So why would it ionize? Because this H over here is positive, partial positive, right? Water is a polar molecule. So Na plus 1 would attract the lone pairs on oxygen, right? But on the other hand, it would repel the H. It's not, I mean, the positive ion is not going to attract the H. So the H is going to be repelled. So in that way, the water molecule might get ionized. The chances of ionization would increase. The H plus 1 might break off. Pascal, is this clear?
Ji, sir.
Yes.
Acha, so the point was, so coming back, the point was that if you have an ionic solid dissolving, I just wanted to show you that both processes are involved. You're breaking the ionic lattice, you're breaking the ionic bonds, and then new bonds are formed with water molecules. The ions are not just randomly floating around, they're actually bonded to water molecules. This is known as a complex ion. A complex, I mean, Na plus 1 aqueous in reality is Na with 6 water molecules that are attached to it. So, next time, I mean, this is a separate chapter that we're going to study later on as well in transition metals. So, always remember whenever you've seen these dissociated ions, these ions are not just alone, they're not just randomly floating around, they're actually bonded to the solvent molecules. So Na plus 1 would be, so any complex ion, I mean, I could show you a lot of complex ions, like for copper. Like if you dissolve copper sulfate, this is what happens. Maybe there would be a lot of images. Okay, just a second. Okay, for example, this one. This is copper ions with NH3. If you dissolve copper in NH3, it's not just copper ions randomly moving around. It's NH3, the lone pairs on N that would be attracted to this copper ion, right? Same with water molecules. So there are a number of solvents in which these things dissolve, and so from all sides, water molecules. This is cobalt. So this is how cobalt ions would look like in water. That there would be 6 water molecules sticking to it. Okay, so there would be bond formation that would be taking place. And so let's leave this here. I just wanted to show you, I mean, this is important. Just remember this one. We're going to come back to this. So what is enthalpy of solution? It's when 1 mole of a substance simply dissolves in water. And it could be exo, it could be endo, and it involves both bond breaking and formation. Now, the other definition that we're going to do is we did lattice energy already. We're going to do enthalpy change of hydration.
Sir, where you talked about dative bonds and you said that the water molecules, there's a possibility that the water molecules might ionize, and you said that Na plus will be attracting oxygen and H is going to get repelled. What about the other H? Wouldn't it get repelled as well?
That can also get repelled. I mean, that is a possibility as well. But the chances are lesser because once this H leaves, OH will have a charge of -1. There would be a lot more negative charge. So Na plus 1 would be attracted to OH -1. Is this clear?
Yes.
H would leave its electrons and the positive H would leave, right? So the remaining part would have excess electrons now. So it would no longer be positive. It would have, OH would have a charge of -1. Clear?
Clear.
सर जनरली सर हम जब सोडियम की बात करते हैं सोडियम एक्वस की तो सर ये जो आपने ऊपर बताया यही चीज एक्सपेक्ट करनी है या इमेजिन करनी है कि जब हम सोडियम की बात करें सोडियम इन सॉल्यूशन और
any aqueous ions, any aqueous ions, whether it's copper 2+ that's dissolved in water or calcium ions that are dissolved in water. This is what the actual picture is. Like the calcium, I mean, if they talk about magnesium ions aqueous, it doesn't mean there's magnesium ions that are just randomly floating in water. It's magnesium ions that are actually bonded to water molecules. Okay? And
Yes, sir.
and the next thing that we're going to talk about is exactly this one. It's basically standard enthalpy change of hydration. Okay? This is standard enthalpy change of hydration. This is probably the last definition that we're going to do. It's this one is known as delta H hydration, and the definition is. As I didn't write the definition of enthalpy of solution actually, or did I? No, I actually didn't. I'll just write it over here. It's the energy released or absorbed. So just writing the definition. It's the energy that's released or absorbed when 1 mole of a substance completely dissolves in water to form an infinitely dilute solution. That simply means a dilute solution, like a very dilute solution. So you're adding a lot of excess solvent or excess water to form a very dilute solution. So energy released or absorbed when 1 mole of a substance completely dissolves in water to form an infinitely dilute solution, and it's going to be measured under standard conditions. So next is standard enthalpy change of hydration. So what is standard enthalpy change of hydration? It's exactly what I just explained. It's when first thing it's always exothermic, and it's always for gaseous signs. It's the energy released when 1 mole of gaseous ions are completely surrounded by water molecules. It's surrounded by water molecules. Measured under standard conditions.
So how do we differentiate? How do we practically differentiate between hydration and this? दूसरा क्या था?
In a solution.
जी जी हाँ
In,
ये वाला.
in solution is the whole process. Solution is you first break the lattice, you break the ionic bonds, up here you hydrate them. Okay, so hydration is this last part only. So hydration is this thing. Hydration is you just add gaseous. This is the final product of hydration. Okay, it's this, and before this you had the same thing except 1 second, but they were not bonded together. So you had let me get rid of these things. So previously you just had water molecules separate. ठीक है इनको तो ले आते हैं. अच्छा, so previously it was just gaseous water molecules, and now what happened is that they got together and they ended up, the sodium ion ended up becoming completely surrounded by water molecules. I mean, sodium ion's gaseous means that it wasn't bonded to anything. Okay. So if something is not bonded to anything, it's obviously in gaseous state. It's free to move around wherever it likes. So this is what's happening in enthalpy change of hydration. That you have an ion and it completely gets surrounded by water molecules. And the reason it's exothermic is because there is bond formation that's happening. And bonds are formed. Is that clear?
Okay.
Just 1 second. So remember, enthalpy change of hydration is this final part that we did. Enthalpy of solution is the whole process. You have to break the bonds, then you form new bonds. So solution, enthalpy change of solution, the tiny part at the end is basically enthalpy change of hydration. And that is for any gaseous ion. It could be Cl ions, it could be any ion. If it gets completely surrounded by water molecules and it turns aqueous, then that's enthalpy change of hydration. Is this clear to everyone?
Yes, sir.
Yes.
So now what we're going to do is we're going to make a small Hess cycle. Okay, and that small Hess cycle is going to be about solution. Okay, and we're going to talk about the same cycle that we just did. But remember, Hess cycle for solution. And only for ionic compounds. We're not talking about compounds like ethanol. We're only discussing ionic compounds. So the cycle is that enthalpy of solution is that you got 1 mole of NaCl solid, you mix it in water and it turns into NaCl aqueous. So this entire process is enthalpy change of solution. The ions get dissociated. Na plus 1 becomes aqueous, and you got Cl minus 1, and they're also aqueous, right? This is what we just discussed. And the process happens in 2 steps, which we have already discussed. What are the 2 steps? The first step is break the lattice, get rid of the ionic bonds. And once you break the lattice, the ions then form new bonds with water molecules. So these are the 2 steps. Break the lattice, you dissociate it, you break it completely, and once you get these gaseous ions should get completely surrounded by water molecules to turn that would be enthalpy change of hydration. So it involves 2 steps. First one, so I'm going to draw the steps over here. The first one is break the lattice. So the sodium ions and the Cl ions are now separate. Not aqueous. I mean, right now I've just broken the lattice. So they're in gaseous state, and they would immediately attract water molecules. And when they attract water molecules, they're going to turn into aqueous ions. Okay, so they're going to turn into aqueous ions. So what's happening here is, this is known as the negative of lattice energy. And this is known as enthalpy change of hydration of both of the ions. Like, it's the enthalpy change of hydration of sodium ions plus the enthalpy change of hydration of Cl ions. Remember your definition for lattice energy. Lattice energy was, what was the definition of lattice energy? It was when gaseous ions get together and they form the lattice. When you're breaking the lattice back into gaseous ions, that's basically the opposite of lattice energy. So it's the negative of lattice energy. So dissolving an ionic compound requires 2 steps. Enthalpy of solution, that's the overall process. You break the lattice and then you form bonds with water molecules. The ions form bonds with water molecules, and that's enthalpy change of hydration. The first part is actually endothermic because you're breaking the lattice. And the second part is actually exothermic because now your ions are actually forming bonds with water molecules. Okay, is this cycle clear?
Yes.
Yes, sir.
Okay, Baku, is this clear? Saqib, clear?
Yes, sir.
Ethan, Mohammed, is this clear?
Yep.
Okay. So this is your cycle. This is your Hess cycle for, like, just like a bond-able cycle. This is your Hess cycle for ionic compounds dissolving in water, and the relationship is, I mean, the reason you have to actually draw the cycle always is because you have to be careful with moles, because a lot of ionic compounds, they don't have one Cl, they would have more than one Cl. So the relationship is that enthalpy change of solution is basically the sum of two things. You break the lattice, that's the negative of lattice energy, or the opposite of lattice energy, plus then the ions that are formed, they form bonds with water molecules, and that's your enthalpy change of hydration. So one of these values is exo and the other one is endo. The first one is actually endo. Don't get confused with the sign. The sign simply means that it's the opposite of lattice energy. The value, in fact, is endothermic. It's positive, actually. And the second value is actually exothermic. It would have a negative sign because you're forming bonds in that case. So enthalpy of solution would overall depend on two things, and these two things would decide whether enthalpy of solution is endo or exo. If the endothermic is bigger, then enthalpy of solution is going to come out to be endo. If the exotherm is bigger than the endotherm, then if enthalpy of hydration is bigger, then enthalpy of solution is going to come out to be exothermic. So remember this: for ionic compounds, it's these two values that are going to determine whether it comes out to be negative or positive. So if it requires a lot of energy to break the lattice, and it's a very strong lattice, then that means it's breaking the lattice is highly endothermic. And if it releases a very small amount of energy when it forms bonds with water molecules, that means overall enthalpy of solution would turn out to be endothermic. So that's your cycle, and you're gonna get questions on this. So I'll just draw, or I'll leave it at this stage. Or we can do a question just very quickly. Let me just find a question. Take 1 second. We can do an example past paper question. It was not this. ठीक है, clear है? Does anyone have a question on this? So I'm just going to do some questions related to this. I think it was the first question in this worksheet. This one. So for example, this one. They're asking you to label this. So remember, ionic solid to aqueous science, that's enthalpy change of solution. Okay, so the cycle could be upside down. I mean, they can make it anyway. So this is enthalpy of solution, like NaCl solid dissolving into aqueous science, so that gives you Na+1 aqueous in dissociated form and gives you Cl-1 aqueous. That's enthalpy of solution. And how do you do that? You first break the lattice, so that's negative of lattice energy, so that you get gaseous ions. So the ions separate, and then those ions are added to water, and that's enthalpy change of hydration, and they form bonds with water molecules. Okay, so it's exactly the same Hess cycle that we just drew. And you'll be given values on this. Just 1 second, if we can find, not this question, just 1 second. But anyway, did the so we can talk about this one. So They've given us this thing, and you're supposed to find it's supposed to find the what are you supposed you use the following enthalpy change of formation values to calculate a value for delta H. I said now this is a different question. I just wanted to do one question. Let me just. I mean, there has to be one question. I'm just wasting. I mean, there was one question initially. Maybe it's another worksheet. A second. Okay, this. So let's try and do this one. He's saying by constructing relevant thermocycles, use the above data to calculate a value for enthalpy of solution. So I'm going to try and do this quickly. I think we have some time. So he's saying enthalpy of solution of MgCl2. We need to find that. What is an enthalpy of solution of MgCl2? It's MgCl2 dissolving. It's MgCl2 solid. It's dissolving. It's turning aqueous. It's going to form Mg2 plus aqueous plus 2Cl minus 1 aqueous. I'm not going to do the calculations. I'm just going to tell you how to do this. We don't have enough time. Now, what's given is what is given in this case is you're given enthalpy of formation of MgCl2 solid, and you're also given the enthalpy of formation of MgCl2 aqueous. I mean both MgCl2 solid and MgCl2 aqueous. So there's enthalpy of formation of MgCl2 solid given an enthalpy of formation of MgCl2 aqueous. Remember, this is MgCl2 aqueous. So enthalpy of formation of MgCl2 aqueous is also given. So if enthalpy of formations are given in an equation, then the formula for that is the enthalpy of that particular reaction would be products minus reactants. I think we would have to do this in the next class then. You couldn't. I mean, this is going to take some time to explain. So let's just keep it till this point. Okay, remember the cycle, and we're going to try and solve that question. And there's a very specific thing that you have to. There's a specific question that comes on this cycle. We're going to discuss that question as well, which is about why does the solubility of sulfates and hydroxides vary down the group in group 2. So you use this thermocycle specifically. So I think in the next class we're going to try and solve that question, and we're also going to cover the answer to that about the variation in solubilities. Okay? So let's do that next time. अभी इतना time नहीं है, not enough time. ठीक है? चलिए ठीक है. कोई question तो नहीं है?
सर ये
हाँ.
आज का लेक्चर अपलोड कर देंगे?
ठीक है, मैं कर देता हूँ. कल मैंने किया था. Let's try and do this today as well. ठीक है?
Thank you, sir. Lattice.
Okay, take care.
Lattice, sir.
Allah Hafiz.
Thank you.
Thank you.